Hello. This one will help with, if you're listening to this and you're doing my assignment, this will help with M3. Blue pen for now. Okay. So the question is, the figure below shows a pulley winding a load. So all that means is this. Here's our pulley. Not a bad circle, is it? There's our pulley, right? And it's winding a load. So it's got a bit of string, let's say like this. And it's got a load, a mass. Like that. Left one. Right. And the load is 150 kilograms there. So that might be different for you, I don't know. 150 kilograms is going upwards. So this pulley is rotating, perhaps going that way, perhaps, and pulling this load up. The acceleration, the centripetal acceleration due to that is making this load go up. So the acceleration, the linear acceleration of this is 2 meters. Right. That's the linear, it's going up, straight up. So this pulley is rotating and then lifting this load up, 150 kilogram load up at 2 meters per second. It's also saying we've got some bearings because we're spinning, so we might have some bearings on here, right? So the friction, the coefficient of friction, right? So you might know this little symbol, that's the coefficient of friction. That is 0.05 because you've got a bearing and things moving, so you've got a bit of friction. The mass of the pulley is 200 kilograms. So in my example here, the mass of the pulley is 200 kilograms. So the load being lifted is 150. The mass of the pulley is 200 kilograms. And it's got a radius of gyration, K, of 150 mil, which is, we've got to be meters, so it's 0.15 meters. Okay, that radius of gyration is like where all the mass tends to act. It's a way of working out inertia, okay? We don't know the radius of this flywheel, so we might have to work that out in a bit. So that's what it is. We've got to find the applied torque. So A is going to be the applied torque. So we're going to be doing this. Total torque is going to be torque to overcome inertia, okay, which we've done before. Inertia of the flywheel plus torque to overcome friction. So we've got a load on a bearing, so we need to do that. That's part A. And then we've got part B, we've got to find the work done. Okay, work done in 1 revolution. Okay, that's quite easy to do. So work done. Put a D there, look, work done. That is just going to be total torque times by the angular distance. We're going in 1 revolution, right? So that's our angular distance. So that's quite easy. And then that's part B. Part C is the power. And power is work done divided by time. We might have to work the time out. That's part C, okay? The hard part, or the long part, is this bit here, really. Okay. So we'll do part A. I'll scroll down a bit, right? I'll do part A. So part A is coming next. Part A, we've got to find total torque. The applied torque, which is the total torque. So we're going to find out torque to overcome inertia and torque to overcome friction. So part A, oh no, come on. Part A, we've got to find the total torque, which is going to be torque to overcome inertia plus torque to overcome friction. Torque to overcome inertia is to overcome the inertia of the flywheel. So first of all, we'll do TI. TI, torque to overcome inertia, is going to be inertia times by angular acceleration. Okay. So we're going to find I first. Now we've got various numbers. We've got, what have we got? We've got radius of gyration. Okay, we haven't got the radius yet, but we've got the K value. So we can use this value here. So we can use, so I is mk squared, not mk Dons, that's the football team. But we can use that because we know the mass and we know this thing called the radius of gyration. The mass of this flywheel is 200 kilograms from the question, times by this K value, which is 0.15 squared. That'll give you value. And it gives me something like 4.5. Okay, you might be different. Okay, that's my inertia. That's my inertia there. Look, everyone's a winner. Okay, that's good. Thank you very much. I've got to find now this angular acceleration. Okay, now I know that this thing is coming up. The acceleration of this flywheel, linear acceleration, is 2 meters per second. There, look. The mass is coming up at 2 meters per second, which means we can say this thing is spinning. A point on this wheel is spinning at an acceleration of 2. Okay, now what we can do is we can use this formula here. So acceleration is angular acceleration times by radius. And we can rearrange that, so we'll do linear acceleration is going to be acceleration divided by radius of the flywheel. Now we know the acceleration because I just told you it. Okay, this here is the radius of the flywheel, which we don't know yet. So we've got to find R first, right? So I'll do it here now. Right? Find R. R is the radius of the flywheel. A couple of things we can do here. Well, there's only one way of doing it, really. We know that another formula for inertia is half mr squared. Okay. So we know all the numbers here. We know all the numbers. I know what my inertia is. It's 4.5. I know half is a half. I know the mass of my flywheel is 200. And I know that's r squared. So you can use that formula to find the radius of your flywheel. I let you do that because it's a merit question. So you need to rearrange this formula, this one here, to find r. The value I get for my example is 0.21 meters. Work it out for yourself, please. It's a merit question. You should be able to rearrange that to find r. So you need to do that. That gives me the radius of my flywheel, which I can put in by there. Okay, so my angular acceleration is now going to be A, which I know is 2 from the question, divided by my radius, which I just worked out. You'll have to work your own one out. 2 divided by 0.21. That will give me my angular acceleration of the flywheel. My example gives me this, 9.5 rads per second. So that gives me my angular acceleration of my flywheel. I'll scroll down. Which now means I can find my inertia torque, which is I times that. So I know my inertia, it was 4.5. Yours might be different. I know what my angular acceleration was. It was 9.5, I think. Yep, there, look. 9.5, yeah. which gives me a number. Turn the page over, my workings out. Turn my page over, workings out. I've got total inertia. That's inertia torque, by the way. Sorry, that's inertia torque. 4.5 times by 9.5 gives me 42.75 Newton meters. This here is my inertia torque, the torque to overcome my inertia. Okay, but we've got to find as well this thing here, look, this frictional torque. Okay, because we've got to overcome inertia and friction. So we've got a couple of things here which we can use. I know that the friction coefficient is 0.05, and I know the mass of this thing being pulled up is 150, because that's going to create a force. Okay, so I'm going to scroll down. So to find now, right, let's get a different color. Come on, different color, let's have that one. So to find the torque to overcome friction, I'm going to multiply the coefficient of friction, which I've just shown you, which is 0.05, I think, in my case, times by the load on the bearings, times by the radius of the flywheel. Because there's my flywheel, here's the load, which was 200, or 150, 150 is 150, it's 150 here. So we've got a load like that, look, it's 150 kilograms, right, which has got a weight in it, and down like that. That's going to be the force on the bearings, because there's bearings making this thing move, see? Right. That's going to be our N in newtons. This number here is 0.05. I'll go back up. Was it 0.05? Yep, 0.05. So, and R is the radius of my flywheel, which I know is 0.21. It might be different. So here we go, ready? Coefficient of friction, 0.05, times by the load on the bearings. The load due to this thing here, this 150 kilograms, which we can convert into newtons, because we know that 150 times by 9.81 will give me the newtons due to that load. So I'm saying that's how much force there was on the bearings, times by the radius of the flywheel, which is 0.21 for me. If you times them all together, this will give me my torque to overcome friction. Okay, in my example, it's 15.4 Newton meters. That there is the torque to overcome friction. Okay, so now we've done inertia torque and friction torque. So to find the total torque, all we've got to do, TT, total torque, is we're going to add now, right, the torque, inertia torque, which is up here. Here, look, 42.75. Yours will be different. Plus torque to overcome friction, which is that number there. Thank you very much. Okay. So ordering, adding them up. So my inertia torque was something like 42.75. Look. So 42.75 plus my friction torque, which is 15.4. 15.4. I reckon that's something like 58.15. So that is the final answer. That is my total torque. That's my applied torque, which is that one here. Look, dun, 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 that one here. Ready, Benny, done it. Okay, that's part A. Okay, I've added up both torques. So my total applied torque is 58.15. That's part A. Done. Thank you very much. All right. Part B is coming up in a bit. Part A is done. Part B is coming next. Part B, give you a different color. I don't know, blue. Okay, so we've done part A. Part B, got to find work done. Go back to the question. Work done is the work done during one revolution of the pulley. Okay, so one revolution. There's a clue. Work done. We know work done, WD, okay, is total torque, which we've done in part A, times by the angular distance. Okay, don't panic. The angular distance, the question says in one revolution. So that's the angular distance. So one revolution, going around like that, one revolution, one rev, is equal to 2 pi radians. That's our angular distance, radians, 2 pi, right? That's it. We haven't got to use SUV or anything like that. So the distance travelled, because we're doing it for one revolution, is 2 pi radians. This here is 2 pi. It might be the same for you. I think it is for the merit question. Well, it is, because I wrote it. Okay, but if it's 2 revolutions, right, it still could be different. Okay, so work done is just total torque times by angular distance. Now we know total torque from part A. And my example is 58.15. It'd be different for you. 58.15 times by 2 pi. Okay, because that's my angular distance, one revolution. That gives me something like 365 joules. That is the work done. That's it. Shock horror. Easy peasy. That's part B. Part B. Okay, so the total torque was the hardest bit. So work done is quite easy. That's how much energy we need if we were trying to make this thing move. If you had a motor or something, or you want to do it, you'd have to put in 365 joules. So that's part B, nice and easy. Okay, part C is going to be the power. How much power we need to lift that. Okay, so that's part B done. Thank you very much. Part C is on the way. Here it comes. Part C. Part C. We've done part A. We've done part B. Part A, part B. Okay, so we've done part A. We've done part B. Part C is the power. Part C is the power. Okay, the power dissipated in lifting the load during one revolution. Okay, so one revolution is the word, because we right, and you also need to look at this here. Look, so upwards from rest. So it starts at rest, which means it starts off at naught. So the angular velocity, right, omega, let's call it naught, right, because it's starting. The starting angular velocity is naught. Hint, hint, right? So we need to use that in a bit. So we've got to find the power to do the work done and to do all of this stuff, yeah? So part C is power. And power is work done, which we know because it's there, look. Divided by, correct, well done, yes, divided by time. Right, because power is how fast you do work. We know work done, it's 365 because we've got it there, look. We don't know the time. We don't know the time. Okay, but we do know this formula, a bit of a suvat. I'll do it in the linear versions because it might be a bit easier. So we know that S equals UT plus a half AT squared. Right? We can use that one. It's the only one we can use, really. We can't use this one, really, because we don't know what V is. I suppose we could work it out, I suppose. No. V squared equals U squared plus 2. These are the linear versions now, right? Just the symbols, but they still work. So we won't use them. We'll use this one. Okay. I'll put it in, right? I'll put it in the angular version now, right? I'll put it in the angular version. So S, angular distance, is that funny thing like that, which we know because that's 1 rev, which is 2 pi. Thank you very much. Equals U is starting velocity or starting angular velocity. Okay, which we know is naught because it's from rest. Times by time. Which is handy because naught times something is naught, so we can scrap that bit. Okay. Plus a half times the angular acceleration, which we know is up here somewhere. Up here. Come on, there. Look, mine's 9.5. Yours might be different. 9.5. Okay, and then half times that times t squared. Look, times by t squared. Okay. So we can use this formula to find t. Now, luckily, because this is naught, so naught times t is naught, so we're going to get rid of that. Makes it a bit easier. So we've got now this. We've got this. Let's use yellow. So we've got angular. No, okay. Angular distance, which we know equals a half times acceleration times t squared. Don't like the yellow. It's not good enough, is it? Blue. So we know these numbers. We've got to find t. Now, this thing here is angular distance. It's 1 revolution, which is 2 pi. That's going to equal a half times by the angular acceleration. Mine was 9.5. 9.5 times by t squared. I don't know t. Okay, you need to find t. Okay, it's a merit question. Rearrange that, please. Don't forget there's a square there, look. So rearrange that, work out t. My example, my time is 1.15 seconds. So all of this thing is done. 1 revolution takes 1.15 seconds. Okay, and my power is work done divided by time. I know my work done is up here, 365. So I'm going to do 365 divided by my time, which is 1.15 seconds from this formula here. You need to rearrange it yourself. It's a merit question. So 365, that divided by that. This is my power. This is the final answer. 317. My favorite joke. What is the unit of power? Watts. What is the unit of power? Or if you want to, joules per second. But 317 watts is the answer. That's part C. Part C done. Thank you very much. I think that's it. It is it, because I wrote the question so I know. Yeah. Part A, part B, part C. Applied torque, work done, and power. Okay. The total torque is the longest bit. Take your time with the total torque. Okay. Because work done is a bit easier because you can just do that, look. And then the power, you've got to work out time. So take your time with that. Take your time. And then power. That's it. That's M3 if you're in my further mechanical principles class. Okay, da iawn. That's Welsh for very good. Over and out.